Okay, let's continue looking at the next section. So I'll comment it in like this and reload. So now we are going to start looking at how to cut things up, because we need to do this if we have our window manager and we have our windows one way, but we want them displayed in a different way. So the main idea here is that of the data type of cuts. So what does it mean to cut up an O into pieces made out of ice? So it means that for every O, we have to say, how can we cut it? And then for every cut, we have to give a list of the pieces of the cut. So here is our running example. So if I have a natural number, then I could think of it as starting at 0 and going up to n, right? Like this. So this is my natural number n. And what does it mean to cut it? Well, it means that at some point I'm going to draw a line, and my number then consists of some k, which is from 0 up to here, and then some l, which is from here up to here. So such that k plus l is equal to n. Right. So this is one way of thinking of cutting a natural number in two pieces, and the pieces are given by the k and the l. And that's exactly what this definition is saying that to cut a natural number, said, well, we find some x and some y using a sigma type, such that x plus y equals z. Right. And what are the pieces of such a cut? Well, it's exactly the x and the y. And here we have the meaning of a cut. So what does it mean to make a cut and then decorate the pieces with some p? Well, it means we choose our favorite cut, and then for all the pieces, we make sure that p holds. And I can strongly recommend that you do this one where you're trying to cut up 12 into 2 odd pieces. It doesn't have to be 2, but it's easiest if you just make it 2. And then you'll understand how this works. And you can see that again, this is actually going to be a functor from I index sets to O index sets. So that's why it's I and O, input output. So that allows us to do one cut, right? What if we want to make many cuts? So if the inputs and the outputs are the same, then we could do another cut after we add one, right? And that's what this data type is capturing. It's saying that, well, you could either stop, but it's useful to have a condition when we stop. So we only allow ourselves to stop if x holds. So you could always make this trivial if you don't want to do that, but that means that you can control what happens when you stop, because often you want to make some cuts until all the pieces actually satisfy some property. So if we stop, then x holds. Otherwise, we can make one more cut, where again we're going to produce many cuts. So that means that we can keep cutting and cutting again until we decide to stop, right? And again, I would recommend that you try it out to see how it works. So here we are starting to see what kind of structure does this many cuts data type support. And it says that if we have some way of interpreting the stopping conditions, so we can go from x to y, and we have some way of interpreting the cut condition where we instantiate the recursive things with y's itself, then we can go from all of many cuts into y's. So if we see a stop, then we can use this one. If we see a cut, we can use this one. And for this to work, there's some all happening here in here, right? So what you'll find is that you will want to use an all map in this definition, but if you do that, then the termination checker is not going to be happy. So you'll just have to re-implement all maps mutually with this, basically. And then if you've done this, then what we get is a bind operation from x to many cuts y, takes us from many cuts x to many cuts y, right? Just by instantiating this in the right way. And then in turn, we could use that bind to implement a map operation. So x to y implies many cats x to many cats y, and a join operation. If we have many cats where inside each cat we have many cats, then we can just flatten these into one many cats. And you should be able to do this just in terms of the bind, one-liner each. Okay, but we also can prove things about these things. So this says that if I try to iterate out of a manycat and I'm replacing all the stops with stop and all the cats with cat, because remember that's what manycat iter did. It said that you had a way of replacing the stops and a way of replacing the cats. So if I do that, then I'll just get the identity function. And that's going to be quite useful. So here in particular, we see that if we compose manycats bind with manycats iter, so that's the one that iterates in general, replacing stops with s and cats with c, and we compose that with just the bind special bind version, well, then we could also do it the other way around. So we start by doing an iter, but now we're replacing all of the stops with this more complicated k followed by another iter. And by instantiating the k with different things and the s and the c, then we can basically prove all of the laws we need in order to show that first of all manycats is a functor, and secondly that this functor is a monad. So that's the finale of this section, that we have made a monad on I index s, which gives us many cats for a given notion of cat.